Aloha, I'm Jim Hagerman, and this is my lab. Today, I'm explaining some of the tips and tricks employed in the Cornet circuit, now in its 4th generation, that make it perform so well and sound so good. Many folks think all you need to do is throw exotic and expensive components at a circuit to make it sound better. Well, yeah, that does work, but only up to a point. If there are flaws or limitations in a circuit, $1 billion in parts won't make it sound any better. Far more important, in my opinion, is topology. Yes, that is what truly matters. But first, please watch my episode 3, linked below, as I build upon that foundation. I spent years learning tube circuits, reading Vacuum Tube Valley, sound practices, and glass audio religiously. In one of them, there was a very interesting tube phonocircuit published by Diego Nardi. I thought it was brilliant, and it became the starting point of my designs. Officially, I did the trumpet first, which employs balanced differential stages. The simplified, single-ended version of this became the Cornet. Here is the Nardi circuit from about 1995. See the red dots? They highlight where my circuit is different. Gain stages are shown in blue, equalization in green, and output buffer in yellow. Obviously, equalization is split passive with no negative feedback employed anywhere. That's what I really liked about this circuit. The Cornet, which appears similar from a distance, isn't. Let's walk through the differences. First, I removed the cathode bypass capacitors. This slightly lowers gain and increases plate resistance, but at the same time lowers distortion, increases headroom, and reduces TBD, transient blocking distortion. TBD is caused by grid current rectification, which only occurs on positive going signal swings. This effect is at its worst when the gain stage is preceded by a coupling capacitor. Large transients in music, especially in the treble region, will cause a temporary shift in DC bias across this coupling capacitor, which then must recover time constants determined by resistor and capacitor values. Transient blocking distortion does not show up during steady-state testing, such as sine or square waves, as it is a transient phenomenon. Another problem, easily remedied, is to bypass electrolytic capacitors with film types. I use polypropylene for this and all other signal paths. Large value electrolytics are needed for power supply filtering down to near DC. However, signal currents of single-ended stages pass through the power supply, hence the need for film capacitors to bypass in the audio band. Everybody should be doing this. All power supply capacitors are part of RC low-pass filters, which greatly reduce voltage noise, keeping amplification quiet. RC and LC filters are far more effective than the brute force capacitor-only banks you see on some equipment. Grid stoppers are always important in tube circuits. Often long wiring or tubes too close to each other can result in positive feedback or instability. This can happen in the ultrasonic region without you even knowing, causing a bias shift or excessive power dissipation. These small resistors solve that issue. Similarly, the cathode follower output stage requires a buffer resistance. Keep in mind, this circuit drives an interconnect, which is effectively a capacitor to ground. Such a load can push a cathode follower to instability as well. This resistance decouples the capacitive load a bit, allowing room for the cathode follower to breathe. One of the key differences between Cornet and every other tube phonostage is reduced input capacitance. This is achieved by lowering the Miller effect, which causes grid-to-plate capacitance to be multiplied by the voltage gain of the stage. Significantly, everyone else places a large resistor where that blue wire is shown, usually to improve equalization accuracy. It also increases noise and lowers gain. This is one of my greatest tricks, as R18 and C11 connect directly to the plate, thereby lowering high frequency gain by a factor of 10. This also reduces Miller capacitance by a factor of 10. Nobody else does this, and the Cornet likely has the lowest input capacitance of any phonostage on the planet, measuring less than 10 picofarads. Why is this important? Because for best frequency and phase response of a moving magnet cartridge, you want to minimize peaking caused by this capacitance. If it is too high, treble becomes shrill, harsh, and leads to listening fatigue. I've already mentioned that equalization is split passive. You could do this in a single stage, but when split like this, you get both better and independent control of each turnover corner. Plus, it lowers overall noise. Not by much, but every bit counts. You see, each EQ network effectively drops treble by a factor of 10. If EQ was done all at once, treble would drop to a very low level prior to the second gain stage, closer to the noise floor, with both getting amplified together. That's why they are split. Finally, I've added a constant current sink to the cathode follower stage, as this improves linearity and dynamics, especially with large output swings. You can hear it plain as day. Here is the measured bandwidth of a Cornet MM flat all the way out past 100 kilohertz. This is exceptional performance for a tube audio circuit, thanks to the tricks mentioned above. That's all for now. Mahalo for watching.